rough fit of the model parameters. So what we're going to do now is use everything we've set up to try and get the model prediction and the data to agree. First, we have to realize that our model does not contain the total number of cases. The Wikipedia data are the total number of cases. Our model has the number of susceptibles, the number of infected, the number of removed, none of which are in the Wikipedia data. However, it's easy to get the total number of cases. I plus R at time t are all the people who have ever been infected. But it's easy to get the total number of cases. It's I plus R. Everybody that has ever been infected at time t is either currently infected or has been removed. So C is the total number of cases as the model computes them, and W is the total number of cases as reported by Wikipedia. Right, so we've got to set up using plots, and we've got to read in the data. So we're going to use this long variable named t-vals from data from column 1 and total cases from data from column 2. The function is as we had it before, so that's our initial setting up. And now we can actually proceed to get a plot. So we set our parameter values. This lambda is the lambda we had before. It's the estimated gamma over 2.2 million. That's the gamma that we estimated. We use dt 0.5. And a final time of 610 days. The initial susceptibles, a population of 22 million. An initial number of infecteds, 50. And an R0 of 0. We set up our number of steps, result values, all of that is as before. This is exactly the model as we had it before. Now we have to make the plot. The C-vals that we spoke about, the total number of cases as computed by the model, is I-vals plus R-vals. And here we plot the model. So this is just plot. On top of the model values, we plot the data values. So t-vals from data. And of course, the length of vector of t-vals from data is just 54, and this is very long depending on our value of dt and our value of t final. This could be a very long vector. So what does this give us? Unfortunately it gives us something quite bad. So the model rapidly goes up to more than 20 million people, basically everybody. And here are the number of illnesses, and this looks basically like 0. So the model is going far too fast. This legend here is also not particularly well placed, but since we don't really know where things are going to go, it's not really going to help. This bit of code here would allow us to put the legend in a different place. So now we interactively change the values. So maybe our lambda was too big, so we could make lambda a bit smaller and see what happens. That's not so great either. So it oscillates. So let's make our initial population a bit smaller. Let's just make that 2 million and see what that looks like. Well, this is beginning to look slightly better. Clearly we need to make our initial population still smaller. So now it's 2 million. Make it 5, so that's now 200,000, and oh dear, that is now far too low. So maybe our lambda is now too low, so we make lambda a bit bigger, and now the model goes too far, but not so bad. You can make lambda a bit smaller, say we make lambda 0.75. No, that's very bad. So maybe our population, our initial population, is still too large. So we make that 100,000, and that seems to be going in the right direction. So we make our population, say, 100,000. Let's make it 50,000. So that's 10 to the 4 for 10,000 times 5 for 50,000, and we see what we get. And things are getting to look better. Let's make this, say, 3.5 times 10,000, and they're starting to agree quite a lot. Maybe we should make lambda slightly smaller. So let's go back to 0.5, and well, now things are beginning to look better. What you can see is that it takes a lot of adjusting. I found by hand these values S0 10 to the 5, I0 30, gamma equals 1 over 8. So we haven't even thought about changing gamma at all. If you change gamma to 1 over 8 rather than 1 over 20, we say that the recovery time is much quicker than it was, but we also know that the Ebola infectiousness is actually concentrated mostly in the crisis week, where you get really, really ill and you either die or you recover. So this value I'll just set at 10 to the 5. This value is that 30, and then the gamma value is the delicate one, the lambda value. It makes a hell of a lot of difference. It makes a lot of difference exactly what the gamma value is. So this 1.47 times 10 to the minus 6 is the one that I fiddled with a lot to get a. And notice that when you have a negative power, you have to put it as a float, otherwise it's a bug. So let's see what happens if I do that fit. And we see, well, that's actually not such a bad fit. One can play with the values even more, maybe change the gamma value, maybe change the I0 values, and you can get an even better fit. So once you've got the best possible fit, that's more or less the limit of what you can do with an SIR model for this data. Of course, there's a lot more to do if you're really interested in the scientific approach to the Ebola virus epidemic, and there's an enormous amount of available literature if you're interested. Search the web.